Okay, so let's look at the different flow regimes that would occur in a flat plate and would occur generally. So you have first the laminar boundary layer that occurs at the beginning. So you start at the leading edge with the boundary thickness expanding as you travel in the x direction, and then you reach a point of after which you start transitioning from laminar to turbulent, and then you have turbulent flow. So in the laminar boundary layer, fluid motion is orderly and it's smooth. The fluid layers slide past each other with very minimal mixing. Velocity fluctuations are negligible. And so the dominant transport method is molecular diffusion, and molecular diffusion is the random motion of the molecules that causes the molecules to collide. And so when you have a lower velocity molecule, let's say closer to the wall, that collides with a faster, higher velocity molecule that's farther away from the wall, what happens is a net exchange in momentum, and that's how you have molecular diffusion in this region, and that's how the influence of the wall spreads in the y direction. Now, what we see here is the velocity profile. So this velocity profile that you could see over here, it's similar to the graph that I've showed you. You can see that the velocity, there's a bigger velocity gradient in the y direction, and it could be described as parabolic-like and steep near the wall. Now, in this region, the heat transfer rates are also relatively low as compared to turbulent flow. And so this is the characteristics of laminar flow. Hello everyone, I'm Amr, a chemical engineer, been working in the engineering consulting industry for about 8 years now. My goal is to bridge the gap between academia and industry, between theory and practice, and give you the tools you need to succeed as an engineer. So if you want to succeed as an engineer, check me out. Now, there are correlations that allow you to calculate what this critical distance is after which the flow will be expected to transition into turbulent, but that's beyond the scope of this discussion. The transitional boundary layer here essentially is just the point where flow alternates between laminar and turbulent, and the region is difficult to model analytically. And by the way, the reason why I didn't put the equation for the distance after which you get the transitional flow is I wanted to keep this discussion on a high level, and we're going to get into the numbers, we're going to get deep into the equations, but I don't want to start confusing you with numbers right away. Having equations in front of you and numbers to fill is the easiest thing, but understanding from a fundamental level what is happening is the most important thing. So after that transition, and once you go into the turbulent region, what actually is happening, and the turbulent region is known for having high inertial forces relative to viscous forces. And so flow is chaotic. You have large eddies that form, and that means that you have continuous mixing and near the wall and away from the wall, and you have strong velocity fluctuations that occur, that get generated or produced in all directions. And so with this kind of behavior, and as you can see here from the small arrows, they kind of represent the eddies that you have mixing all over the y direction. And in this case, the main dominant transport method is turbulent mixing. It's not molecular diffusion anymore. And because you have really good mixing, the velocity profile here is a lot flatter. And so you have a more flatter velocity profile. However, you still have that very steep velocity gradient near the wall. And that means that you're going to have higher shear stress, because if you remember the shear stress equation, shear stress is equal to viscosity multiplied by the velocity gradient evaluated at the wall. So the steepness of this gradient will determine the amount of shear stress that is produced. Now in this turbulent area, heat transfer is dramatically enhanced. And so that's why if you want to improve heat transfer in a lot of applications, you want to make sure that you have turbulent conditions. Okay, so I want to highlight that the transition occurs when the inertial forces overwhelm viscous forces. And if you remember from your fluid mechanics, usually a transition from one flow regime to another can be defined by looking at the Reynolds number. And we're going to look into Reynolds number further on in this section. But for those of you that know what Reynolds number is and are aware of that, you remember that after some Reynolds number, the higher you go, then the more turbulent the fluid becomes. And that's because the inertial forces overwhelm the viscous forces. And so here, the velocity gradient at the wall is steeper for turbulent flow. And so you might actually expect to have higher shear stresses because of that. And correlations exist, as I mentioned, to calculate the length after which the fluid flow is expected to transition from laminar to turbulent flow. Okay, another important point is that the wall velocity gradient, and therefore the wall shear stress, varies along the length of the surface of the flat plate. And I did mention that to you previously. But now that we're looking at the different regimes, let me actually explain what's happening here. So for the laminar flow over a plate, so in this section specifically, you have that the velocity gradient at the wall is largest near the leading edge. And I've shown you an example of that, where I showed you two arbitrary points in, let's say, the laminar region. And we saw that the region closer to the edge had a higher gradient, and so it would mean that it has a higher shear stress. So for laminar flow over a plate, the velocity gradient at the wall is largest near the leading edge of the flat plate, and so it gradually decreases with distance downstream as the boundary layer thickens. And so as a result, the local shear stress decreases with distance from the leading edge, and I showed you this equation. Now, this trend does not continue indefinitely, and that's because you have a flow transition that occurs from laminar to turbulent. And when that happens, you have enhanced momentum mixing near the wall, which causes a sudden increase in the velocity gradient, leading to a sharp increase in the wall shear stress that happens when you transition to turbulent flow. Now, farther downstream in the turbulent region, you have that same trend where the local shear stress again starts decreasing with distance, but remains significantly higher than in laminar flow. And I'll show you an example actually. So this is an example of a paper that I found, and this figure likely shows the local friction coefficient of a plate as a function of Reynolds number. And since Reynolds number for a flat plate increases with distance from the leading edge, then the plot represents how wall shear stress varies along the plate. And because the skin friction coefficient is proportional to the wall shear stress, then the behavior of the curves in this plate directly reflects the behavior of shear stress along the plate. So essentially, I found this example in a research paper, and this example shows the local friction coefficient. It doesn't show you the local shear stress, but I know that the local friction coefficient is proportional to the local shear stress, and so essentially you can track the trend of the local shear stress by looking at how this plot behaves. And this is the Reynolds number. It is not the distance from the leading edge, but also because I know that the Reynolds number for a flat plate changes proportionally with the distance from the leading edge. So essentially, you could look at what's happening in this graph, and it would pretty much mirror shear stress versus distance. Also, I want to note that because the wall shear stress varies along the surface and the local friction coefficient also varies with position, then to characterize the overall resistance to flow, an average friction coefficient needs to be defined. And so that could be done, as I mentioned previously, by integrating the local friction coefficient over the entire length and dividing by the total length. That would give you an average friction coefficient. For example, the friction factors used to calculate the pressure losses in pipe flow represent actually average values. They're not local values. And a similar distinction between local and average quantities will arise when we discuss heat transfer coefficients in thermal boundary layers as well. So what you'll find is we're mostly interested in average coefficients. So we're interested in average heat transfer coefficient. And in the case of the flat plate, we'd be interested in the average friction coefficient. And this is what we're going to be using in our equations, but it's good to know the difference between the local magnitude and the average magnitude. So now let's talk about the thermal boundary layer. Actually, before going into the thermal boundary layer, I want to clarify something. Earlier, I gave an example to explain why the shear stress decreases in the x direction in the laminar region. We said this happens because the velocity gradient at the wall decreases as you move downstream. And the reason the velocity gradient decreases is that the boundary layer thickness keeps on growing. And as the boundary layer grows, the influence of the wall extends farther into the y direction, so the velocity change from 0 at the wall due to the no-slip condition to the free stream velocity now occurs over a larger y distance. When we talk about the transition to turbulent flow, we said that there is a sharp increase in shear stress. This is because turbulence increases mixing, which brings high velocity fluid closer to the wall, and as a result, the velocity gradient at the surface now becomes much steeper. In the turbulent region, we said that the velocity profile is flatter compared to laminar flow, and this flatter profile is caused by the stronger mixing in the flow, which makes the velocity more uniform across most of the boundary layer. However, flat here does not mean perfectly flat. Even in turbulent flow, the boundary layer thickness continues to increase as we move downstream. Remember, the boundary layer thickness is defined as the y location, so the distance from the wall where the velocity reaches 99% of the free stream value. And since the velocity only reaches the free stream value at the edge of the boundary layer, this means there is still a velocity gradient throughout the boundary layer, even in the turbulent regime. So at this point, I think it's a good place to pause and look more closely at what is happening inside the turbulent boundary layer itself. So in turbulent flow, the boundary layer can be divided into 3 distinct zones or 3 distinct layers. Closest to the wall, we have the viscous sublayer. Now, in this region, transport is dominated by diffusion, and the velocity profile is almost linear. Most importantly, this is where most of the velocity change occurs. So the velocity goes from 0 at the wall due to the no-slip condition to a much higher velocity over that very small y distance. Just above this viscous sublayer, you have the buffer layer. In this region, you have both diffusion and turbulent mixing are present. The velocity is changing with y, but not as rapidly as inside the viscous sublayer. Now, farther away from the wall is the turbulent region where transport is dominated by turbulent mixing. Now, in this region, the velocity profile becomes relatively flat, meaning the velocity changes only slightly with y because the flow is already closer to the free stream velocity. So when we say that the turbulent velocity profile is flatter, we are really referring to the buffer layer and the turbulent region, not the viscous sublayer. The viscous sublayer is still very steep, and it is the behavior of this viscous sublayer near the wall that controls the wall shear stress. And so most of the velocity change in the turbulent flow happens very close to the wall, inside this viscous sublayer. Now above this region, the velocity still increases with y, but the change is much smaller because the flow is already close to the free stream value. As you move now downstream along the plate, the boundary layer thickness grows, as I mentioned. The wall is now separated from the free stream by a larger region of slower moving fluid. Even though turbulent still mixes the fluid reaching the wall, the fluid near the wall has a lower velocity than before. And so because the fluid reaching the wall now has a lower velocity, the velocity gradient at the surface decreases. And as a result, the shear stress generated at the surface becomes smaller. And so as the boundary layer continues to thicken and grow in the x direction, also the viscous sublayer grows as well. So to summarize, I want to emphasize this again. Even though turbulent flow has a flatter velocity profile and a higher shear stress than laminar flow, however, analogous to laminar flow, the shear stress in the turbulent region also still decreases as you move along the plate. Okay, without further ado, see you in the next video.